Thanks a lot. Welcome. I'm going to scroll away from this, but I'm going back to it in a minute, so no worries. This is me. I'm from Germany. This is my Twitter handle. In German, it's very funny, but in English, obviously not. The slides are there, but they are not important. I have just 5 slides, and then we will switch over to the notebook. This is about convolutional neural networks, like networks that work on images, and we're using Tensorflow and then Keras as a front end to Tensorflow. Okay, what is the challenge of today? We are trying to recognize speed limit signs. And this is not like rocket science, because luxury cars, I don't own one, but at least German luxury cars have been able to do this for at least 10 years. And this is how they look like. I just downloaded from somewhere a pretty reasonable size of speed limit signs, and they are very bad quality, as you can see. Who knows what is this? 100, right. Oh yeah, okay, it's 100. Sometimes it's not even easy for us to recognize them, but this is the training material. We have a limited number of samples, so you have 79 of those, 81 of them. So this is very limited, especially for the endeavor of training image recognition. But we only have detailed views. So all of these speed limit signs, they're in the center of the picture. And this is important, because otherwise we wouldn't be able to do this. Okay, it's inspired by a blog post by Walid Abdullah. And he did all the coding for preparation. So I more or less took over a lot of the code that actually made this, those images processable in the first place. So big thanks to Walid, and also kudos to him for doing great work. So my stuff is based on it. So first of all, it might be surprising, but there's no installation necessary. You could follow along using your mobile phone if it's halfway okay. So it works on my Pixel. I tried it this morning or yesterday, but it's actually not recommended. It's not advisable, but it's possible. And what we do, we host the notebook on Azure Notebooks, which is provided by Microsoft. And I don't know why, but they let you run very powerful notebooks on their servers for free. I don't know why, but it's a nice gesture. So there's no local installation required. It is possible to do a local installation, but it's totally not advisable, because at least compared to my machine, this notebook hosted on Microsoft servers is at least 10 times faster than my local machine. I don't know how they do it, but they do it. So this brings us again to this step. Who wants to follow along by really actually executing the code? Like half. Do it with this thing, right? Do what's said here. Do what's said on this slide. And while you do it, and I also heard that it actually works. If you follow these instructions, it actually works. And while you do it, this is the only thing that you actually have to type in, and then you do certain steps. While you do it, so it doesn't get boring, I will show some code already. But first, if you did this on your local machine, running on battery, it wouldn't work. I mean, the battery would be drained in half an hour. It's a very computation-intensive thing that we're doing. So don't do it on your local machine. Do this. For the people who are not like installing right now and who are a little bit bored, as I said, I will do some entertaining stuff in a minute. But first, I want to make sure that everyone have typed in those link thingy.
You do the clone library thing.
You clone, right? So, well, I could do it. I could do it. Wait. I could do it together with you. Let me see how I will do it, but I will. So I'm just pretending that I'm totally new. So this is what you do. This is what you see this is the notebook view. This is the way you see it when you're not logged in. Because now I'm also not logged in. Then you click on the workspace. You can already see the notebook, but you cannot execute the steps. This is something that's also possible on GitHub. That's not something very fancy. But what you can do now is you click on the clone thing here. And when you do this, unfortunately, you have to do some steps, because they now want to know who you are. You now have to log in. I'm zooming in a little bit. So the Wi-Fi is exceptional. I mean, big kudos to Bloomberg, obviously. You do something like, unless you have a Microsoft account, any Microsoft account is OK. You click on create new Microsoft account, and then, unfortunately, I've used like 10 of my email addresses already to try this out in different scenarios. I think I have one left. So you do this at apache.org. I have no idea. Something. Oh, be sure to uncheck this, right? You don't want promotion. It's totally free of cost. Oh, holy goodness. That's tough. And that's the hardest thing, right? To find a password that actually works. No idea. Probably I can't remember now. So click next. And then what they do, they email you a code. And then you enter the code, and then you're good to go. It might take a minute or two. Let's see if my email has already been delivered. Let's see. Oops. Maybe it's in the spam folder. No, it's not. But from now on, I mean, I would just pretend it worked for me. It might take a minute or so. It's all very like private and shouldn't be read by you, but most of the stuff is in German, so I'm safe, I think. I'm sorry. Oh, it's credit card. Not good. I will scroll away for a second. So, yeah. Sorry? Promotions part? OK. Yeah. OK. Who's still waiting for the confirmation code? No one. Who has any problems? That's impossible. No one has any problems. The only one who has problems is me. OK, then I'm blown away by this. I've never experienced anything like this. So it doesn't work for me. It works for you. Good. Better than the other way around. OK, now the setup actually worked in 10 minutes. I'm blown away. So if you don't want to follow along on your own machine, that's also cool. I will show each step. We don't need this. Just some simple guidelines for the notebooks. That's the only slide on notebooks. It's composed of steps, and the step is either markup or code. You can edit all the steps. It's like real code, and you type enter to edit it. You can have code completion, typing tab. I will show it in an example. Prefixing your code with an exclamation mark makes it a shell command. So this is a Unix system running underneath, and you can do whatever you want. You shouldn't do certain things, but you can do everything more or less. Shift and enter executes one step and jumps to the next one. And shift and enter executes one step and creates a new empty step after that. So that's all you need. And while I type, I will explain what I do. OK, this is just a set of links. That's all basically I read. So my background is I'm a programmer. And it took me a long time to actually dive through all the very, very interesting, but also very frustrating world of convolutional networks. And I hope to save you some time by showing you and then sharing experience. OK. Now I'm switching to the notebook. And this is the notebook that you have open. You should recognize it. Hopefully I'm finding it. Okay, I have to scroll up. Is it large enough? Is it okay? Can you read it? Good? Hands up who can't read it. You can't read it. Leave it, okay. I don't know, it takes a while until actually zooms in. I don't know, but it should be, it's working. Oh, there you go. Good. I don't think I can make it any bigger because otherwise I don't know what I'm doing anymore. So what we do first is that we install all the dependencies that we need. And what we also do is we pre-process the data. So what I'm doing now, I go into one of those lines. I hit Shift and then Enter. And what it does, it executes the commands, right? It should look the same on your machine. This was just text. And this works very fast on my machine, on my netbook. But it should be slower on yours. This is installing scikit-learn. Who does not know scikit-learn? No one does not know scikit-learn. OK, perfect. So this is just to help our thing to split test from training data. We rarely use it, but just a little bit. This is just a helper for me to see if everything's fine. I'm checking the versions here. And the scikit-learn version should be at least 0.18.1. Not sure why it doesn't work for me. Maybe it doesn't like me. And just to let you know, when there's an asterisk here, a star, then the step is executing at that time, and you need to wait. And this is executing right now. It should be a very fast operation. So I'm wondering why, but because it went so smoothly before, I'm not mad at all. Not yet. So maybe it actually worked, and it didn't tell me. It's also sometimes the case. Well, you do the same thing, right? You scroll through the stuff. You try to install all the stuff, step after step. Maybe I was too fast at one point. I don't know. Just one trick. When you have the impression that your kernel sort of doesn't like you anymore, then you do reconnect. You shouldn't do restart, because then you lose all the state of your notebook. So don't do this. Just use restart. So if it doesn't work for me, I will. It seems it doesn't. Oh, it does. Oh, I was too impatient. Sorry. I am impatient. So the next thing that we're installing, and this is the main thing, this is called Tensorflow. And Tensorflow is a very low-level library. And all it can do is you define tensors. And a tensor is something like a higher dimensional array. So a tensor of one dimension would be an array, of two would be matrix, of three it would be something like hard to imagine, 4, 5, and so on. And it can actually execute operations on that. And those operations are typically very expensive to compute. But we don't care, because TensorFlow does it for us, and it also can make it run on a GPU. And I suspect that the Microsoft people actually execute all that stuff on a GPU, because it's so fast. However, TensorFlow is very powerful, but it is very tedious to use. You don't want to work on the level of tensors. You don't want to, at least I don't even want to understand what a tensor is. I had to, but why? I want to do machine learning. Because of this, what we do, we install a second library that sits on top of TensorFlow. It's called Keras. And Keras gives us high-level APIs where we define nets, where we define optimization strategies. And this is the level that I'm confident with, that I think that's cool for me. So Keras I did install. And they recently released version 2. And I prepared all that using version 1.2, but it seems that's all just cool. So version 2 seems to do just the same stuff as version 1. It also tells you a lot about wrong models, and it's very, very helpful. I would never use TensorFlow without Keras when I do machine learning. And again, reference to the great article that I took some of the code to pre-process the images from. Great stuff, just big fun. OK, so first step, we need to understand the challenge, like how hard is it, and we need to prepare the data. I have data somewhere, and I'm downloading it right now. That's possible on Azure Notebooks. And there are links how to do it. I just use curl here. Curl is something that works on Linux, uses normal HTTP stuff, and I download the data from here. It's there. It works. Next thing, I'm unzipping it because it's a zip file. This is all boring. This is just preparation, not machine learning. And I have a look at it. Now it gets more interesting. I unzipped it, and you see there are 5 directories. And each directory has a number, and that number is the label. I set it up like this. So you find some images in here, and there, and there, and there. And the directory names serve as labels. And I described it in the README. Oh, that was bad stuff. No, it works. I was afraid I was navigating away. So in Germany, there's actually 30 kilometers per hour. And I think you have 20 miles, right? So this is German science. Then we have 50, we have 70, 80, 100, 120. And as you know, beyond that, on German Autobahn, you can go as fast as you want. So there are no speed limit signs beyond that. This is already quite fast, but it doesn't matter. So I have images, and how do they look like? This is, again, still preparation. They look like this. They're in the PPM format, which is totally obscure to me. I've never heard of it. Anyone heard of PPM image format? Ah, what is it? I mean, why?
Binary.
Sorry?
It's binary and it's ASCII binary. So
Oh, it's ASCII binary. Well, it took me a long time to actually find anything that could open it. That was a tough. Sorry? I don't know, but what actually can work on it is a scikit image, so good stuff. So what we are doing, we are preparing stuff. And this code, you just ignored. I just copied it from the other guy from Berlin, and it helps us loading that stuff. And now that's interesting. We have the labels in here, and the images in there. And what we have 6 labels. You see it here. I think I need more space now. I'm getting annoyed because, better. OK, what you see here, you have 6 labels, and we have not even 400 images. That is a toughie, because typically training on image data, that's my experience. And that's also what other people tell me. You need a lot of data, but we don't. We don't have a lot of data. So let's see. Let's see how they look like. You already saw that in the slides. That's how they look like. And as you can see, we have different amounts of labels for each of those categories. For this, we just have 41. For this, we have 81 for the 50. So it's also not evenly spread. And also, they're not normalized. So some have this shape, 39 by 38, and they all have 3 color channels. And also their intensities, like how they are spread, is also not normalized. But that's very bad for training, because this gives us variation where actually there is none. I mean, there's no difference between something of this, the resolution of this. So what we do, we actually normalize this. And this is where scikit image comes into play. And scikit image has a transform function and transform object, and you can use the resize function, and we resize all of them to 64. And that's also mandatory, because when we feed this into our neural networks, they all need to have the same size, because we have to specify the amount of nodes that we are feeding in. So now we have all the images in 64 times 64 and 3 color channels. and all the values in the color channels are between 0 and 1. So they're normalized now. This is also like very technical preparation, and still not machine learning. But it's mandatory, we have to do it. Okay. Oh, by the way, if there are any questions, do not hesitate just to ask. You can also post it in that channel, but then I don't see it until later, okay? So if you have questions, just ask. So now, what we're using is NumPy, and you probably know it. It's the basic library that provides us with data structures. And those data structures are shared all over the area of machine learning. And what we're doing is we transform the labels, which is 1, 2, 3, 4, 5, and the images, we transform them into NumPy arrays. And it's common to name the labels with a lowercase y, and the training material with the uppercase X. And the shape, I think that's pretty obvious. We have 379 labels. And we have, matching to those 379 labels, we have arrays of 64 times 64 times 3. This is this. So this is how our data structures look like. So the first, and probably the hardest, if the only hard part, I'm not sure, is choosing the right architecture. This is super hard. It's also not a solved thing where you just, where you just Google and then, oh, not good. Where you just Google and then eventually you find the right solution, because everything is different. Well, what do we do? So first of all, some technical stuff. Not good. It should work. I mean, technical difficulties. I think it will work eventually. So I'm not worried. So first, what we have to do, we have to turn our labels into categorical stuff. That is just technical. You have to do it, otherwise it doesn't work. So, and if you looked into this thing, it would look. You may make sense out of it, but it's not worth it. So just don't try. So what we're starting with, and this is quite good that it doesn't work right now, because you see it's still executing this very, very, very simple step. It shouldn't take a second. But that doesn't matter, because we just go through it, because I wouldn't execute this anyway. So
you said you had to convert them to categorical. Can you just provide a short overview of why?
Because, well, I'm not good at explaining this. Otherwise, it doesn't work. That's a bad explanation, right? So how it looks right now, it's just a number, like 1, 2, 3, or 5, or 0. And now it turns it into an array, where in each of those, well, if it actually executed, I could show how the new data structure looks like. It converts it into an array of arrays, and in each of those arrays, there are a bunch of zeros and 1, and that 1 like represents the real category. It's just a technical thing to make it work. That didn't make you any smarter, right?
Maybe it's a scaling issue, or
no, it's.
You want to represent these as probabilities of those categories?
Yes, it's probabilities, but all the probabilities are 0 except 1, and this one is 1. So it's just a technical thing. Unfortunately, well, it doesn't like me anymore. Oh, it does like me. So we can actually do it. So it looks like this, right? As I said, for each of the categories, we now, that used to be a 1, right? This used to be a 0. This used to be a 0. Also 0, 0, 0. So it's turned into this data structure just for technical reasons. It's boring, but we have to do it. And there are a lot of things in between. So don't think that this is all just ones and zeros. There are a lot of things in between. And it used to look like just an array of numbers. OK, so now works again. Good. But we still don't execute this, because it takes a lot of time, even on Azure, and it doesn't help us. So don't execute it, unless the parts that I'm actually explicitly telling you to execute. So first what we do, we create a single layer neural network. And this is how it looks like. So this is just technical stuff, imports. This is not technically really a layer, but no, the other way around. Technically, it works like a layer, a neural network, but it's not. It's just defining how the input looks like. And you already know, 64 times 64 images with 3 color channels. One for red, one for blue, one for green. And now we take this and put it into a fully connected layer. Who does not know what a fully connected layer is? OK. Oh, I had no idea. Oh, OK, good. Then I have to explain it, right? So this works as an input. It's a layer. That means, well, I'm not very good at drawing. You will see it, but I will do my very best. So this is one image, another one, another one. They're all 64. Sorry. Especially bad at drawing at this thing here. Times 64 times 3. Because there are 3 color channels, right? Now you feed it into something. There's one layer that can actually accept that stuff. And now, what that input layer has, it has 64 times 3 input nodes. Some people get bored, I see this, but I have to do it. And now, it feeds it into the next layer. Those are neural networks, and we have layers in them. And the next layer, it actually has 226 nodes. 56, sorry. 256 nodes. And I can't draw them for obvious reasons, right? But I'm drawing like a few of them. And how this works is that each of those input nodes gets connected to all of those input nodes. And that's why it's called fully connected or dense. So that means this thing gets connected to this also, this thing. You see what I'm doing? It's probably boring, right? So, and then next thing, that means you get a lot of connections. And this is the input, the first layer. This is a so-called hidden layer. And then once we've done that, I connected all of them to all of them, we also have a final layer. And the stuff in between, we just ignore for now. And this is the prediction layer. And it has 6 neurons. This time, I might be able to, no, I'm not. 4, 5, there's the 6th one. And now, each of those nodes in this layer connect to those output nodes. And they have the so-called softmax activation. That means what they actually output is a probability that I think should add up to 1 if the input, like this thing here, to what category it corresponds. So say I feed in a 30.
So what determines the 2, 5, 6, and the 6?
Give me a second. I'm just finishing this. So I'm feeding in a 30, and it should like give a probability of, say, 1.9 here. This would be 0, this 0, and this 0. Maybe there's a 0.1 somewhere. The question, I'm sorry.
Yes. So what determines the 256 and the number 6 would be?
Perfect. So the question is, how did I find out about these numbers? Those are obvious, right? This is just how my input looks like. This is just guessing. This is just wildly guessing, just taking something. And I'm telling you a secret, it doesn't work at all. So this I have something that works, no worries. But this doesn't work at all. And this is not only me. I've been told that this is the life of the most people who do this. You try things out. You read literature. You try it. You do an experiment. I will show the experiment. And then you see it won't work. And this doesn't work either. So this is a very bad number. This is very bad architecture. But it is a very simple architecture. Now for the 6. The 6 is very important because I have 6 categories. So this is my input, and I want to map it to the output, to the 6 categories. I want to feed in 30, and now I want to get something like a probability of how probable or how likely is it that this actually is the 30. And this is because the 6 is fixed. So the 6 is a good idea, this is a good idea, everything is in between is a very bad idea. But it is simple. So all the other things that we're trying a little bit later work very similarly. And I have to apologize for my bad drawing, but it doesn't get any better. So what we, oh wait, I forgot something, right? No, I didn't forget anything. So this is again just syntax or technical requirement for Keras. We create a model, and the model, it represents the architecture of our network. And you get this inputs thing, and you get this as the output, and the model is defined. You can see the input shape, which matches this. You can see the output shape, which matches this. And this is the only thing that will not change when we make our model better. OK. Don't execute this.
What's the significance of the num value in the first element?
This thing, I actually don't know. Is it the batch size? Ah, good point. Good point. Batch size. So we will, in a minute, well, I'm actually executing this now. So in a minute, we will actually use this to train, and you're right. Then we will actually see that we're feeding in batches of data. Good point. Thanks. But first, before we do this, we have to compile the model. And this can be compiled to either TensorFlow or what's the other thing? Help me. Theano. Theano is the other one. So Keras can actually interface to different backends. And we are using TensorFlow here. But I think that the default is Theano. So that means you define your model, and you can make it run on TensorFlow, and the same model you make it run on something else. So I have to compile it to this. And this is just the loss function. That's very mathematical. I don't understand any of the details of it, to be honest. And it's tricky. So I read a lot of what the Stanford people write, and it always gives me the impression I'm not smart enough to understand it. So maybe you do, I don't. But you have to set it like, this is the right thing to set because it's categorical. We measure on accuracy, or accuracy, I think, to see how well have you trained. We could also measure on loss, but we're measuring on accuracy. Then there's optimizers, and this thing here, RMS prop. I always use the SGD, but people keep telling me this is the best thing. No one knows why. It hasn't been scientifically published, but everyone keeps telling me you have to use it. And it's impossible for me to understand it, like never. It's a very simple mathematical thing, but I still don't get it. And as I speak to very smart people, I get the impression they don't get it either, but maybe that's mean. And it's just, from my experience, it's just like trying out a lot of things and see what works best. Like a very, I don't know, engineering approach. I'm not quite sure if you agree, but if anyone actually understands it, then talk to me later. So these are the standard optimization things. I always use this because I was dumb. I had no idea. But this is actually the right thing to do. And this is just a way to tell you, like to visualize, that's the best that I could find, how they try to, this is a saddle here, and you want to find the minimum, how the different optimization strategies, how they proceed from this. And this is very bad because they have no idea that they should go down here. This is way too fast. And this always looks like it's the best. So it slowly and very decisively goes down here. And why is that important? Because we want to actually, when we try to train our model, we actually want to have very good results, and it should actually find the minimum. So it's always about minimizing the error in the network. And this seems to be the most promising thing. And there's a second, yeah?
From that visualization, how do you know that RMS prop is the best?
Well, looking at this is obviously not good. They are slower. And it looks like, well, maybe this is also good, right? Depending on what. So it's if you look at it, if you want to go in the direction of the minimum, and you want to be very good at it, well, right, you don't see it here. Maybe you see it on the next visualization. But you can see it's better than gradient descent, right? Because gradient descent sucks, and the green one also is very bad because it takes a while until it finds out it should go down. This is also very bad. Maybe one of those is the best. Because at least they very quickly go in the right direction.
Sorry.
Yeah.
What is on the axis?
Oh, it's
Why is there, the axis?
it's just something. This is just a made-up function that you're trying to optimize, to try to find the minimum. It's just something. It would be typically this wouldn't be two-dimensional because that would mean we just have two parameters. Would we have like thousands of parameters, and each of these things would be a parameter for a neural network. Now we're trying to minimize like the loss of that network, and this is like the height of this saddle is like the overall loss of this thing. And so you want to find a minimum.
But this is just a generic animation. So
Yes.
nothing to do with your actual model.
Yes. So it's just generic.
So that whatever gradient descent algorithm you use, this bears no relationship to what you're actually
Right.
doing.
So this is just generic stuff.
It's just a very particular saddle point.
Yes.
Showing perhaps eta delta is the fastest.
Right. So eta delta gives the fastest, but it might be too fast. Yes, right. So this is just generic. Why am I showing you this? Because this is the best explanation that I found on the net. So showing you the mathematical formula is very small, very simple, but totally incomprehensible, at least for me. This also is a second visualization, also generic, and it shows this is supposed to be the actual minimum. This is supposed to be gradient and all that thing. And this is just the visualization, how they actually find that minimum. So you could also argue that this is better, or the black or the blue one, but it's always these three. And as I said, people of much more practical experience say, use this and you're on the same side, on the safe side. So hopefully that wasn't too confusing. Let's see. So maybe that was too much detail. I'm not sure. But what do we actually do? So to find out, is the architecture actually sufficient? What people do that are smarter than me, they do some sort of sanity check. They use a very small fraction of the training data, like 5% or something. That's what I'm also doing. I think I'm executing this because I'm brave today. And now, oops, wrong. Is this from my code? That's not good. Well, does it work for anyone else? Yeah? Obviously, I messed up my notebook before. So no worries, because the results should still be OK. So what we see, we now have approximately 5% of 400. That means 20. And what we're doing now, we try to overfit our model, which means we try to get 100% accuracy. That means we're trying to use the architecture to actually perfectly fit our training examples, which are just 18 or 20 in our case. And if this doesn't work, we can be very sure that our architecture, oh no, not very sure. It's a strong indicator that our architecture is not sufficient to actually solve the whole thing. And it might take a while, even on Azure, that's why I'm not doing it. And I can tell you, it's stuck on accuracy. It doesn't move at all. It's very low accuracy. You could argue, and you never know, that if I just keep on training, it will eventually have a high accuracy. But I doubt it. So first, what we do is something new here. So we have the model. I pass in I didn't explain this well, sorry. I pass in some training data, and I pass in training labels. This is the batch size, like how many of them do I feed in at once? And it's subtle how big it should be. Some people say if you make it too small, you tend to overfit. If you make it very large, you need a lot of memory. So it should be somewhere, again, something you try out. I have 300 values, and I feed them in batches of 100. And I'm training for 50 epochs. How do you pronounce that in English? Yeah. Epochs? Yeah. That means I do this same thing 50 times over and over again. Same thing, 50 times. And here you see one of those epochs. This is 93. And you see this is the loss. That means the overall error. That is a little bit abstract. And the accuracy is much easier to understand. How many of them do you actually train correctly if you check them? That means just 20% of them work. And it's stuck at that value. So not good. Fully accurate would be 1. And this should be totally possible. This is just 20 of them. This is just, it should be totally possible to accurately represent them. It should be 1, right? And it's not. And it's arguably, maybe it's just because I didn't try enough, but most likely it's not. So it's just not a good architecture. And this comes back to the question that we had a little bit earlier. How did I come to this 226? I was just guessing. But what I'm doing now is I make my network stronger by putting in more than 1,000. And theoretically, which you can read here, also something, the proof I don't understand at all, but what the proof says, I understand. It tells us that it's possible with just one hidden layer to represent any function. That means, theoretically, if you make this large enough, and you actually get it to train to behave the way you want, one single layer, one single fully connected layer is always sufficient. Practically, it doesn't work at all. But theoretically, it could. It doesn't work at all. And this is also very, very hard, and it goes over my head. But it's a matter of how do you train the whole thing. And you just can't. Well, not with the mechanisms that we have. So I did this. This time I'm not letting it run. No, the other time I also didn't let it run because.
When you say hidden layer, what do you mean?
Hidden layer, oh. I think I put it before, but I will show it again. So in a network, the first layer, it's a network, it's composed of layers, is the input layer, as I drew before, right? You feed in the images, 64 times 64 times 3 color channels, and then you have the output layer. And this was the 6 categories, you remember, as 1, 2, 3, 6. And in between, there may be something. And typically, in between, you have many more layers, and those layers are called hidden layers. So we have just one layer in between. It's fully connected. That means all the inputs go to all these nodes. And this is called hidden layer. And we have just one. And as I said, mathematically, it's provable that 1 is enough, theoretically. But it's in practice, no. So this also doesn't work. So I made it bigger. I made a higher choice. It doesn't work. And it's not as desperate as the one before. So I see improvements. With the one before, we were stuck at 22%. And now we're stuck at 28%, which is also very bad. It's totally not sufficient. You see, I'm not cheating on you. I tried it for 100 epochs. What people tend to do, and what turned out to be a good idea in practice, is add more layers. One hidden layer, second hidden layer. And you split the numbers of neurons to those 2 layers. And then we have 2 hidden layers. I mean, I think it's obvious now, but I'm still drawing it now. Input layer, output layer, 1 hidden layer, 2 hidden layers. And those are still fully connected. It means all of those input into all of these. So you have a lot of connections. You have a big model. And How much time do I have, by the way? Well, when is this over?
150, so you've got 47.
Oh, that's great. So by the way, if it's boring or anything, or you want to do something else, then tell me. But we have plenty of time, and I'm very happy about that.
You never actually explain what flatten means. Could you briefly say what that means?
Oh, right. So I used flatten before. I'm not actually sure if I have to do it here, but what it does is typically, well, we would have to wait. That's a very good question because it concerns the shape of the data that flows through our network. What is the shape of the data that flows through our network? And I was actually asking the very same thing to myself this morning. That's why I made some experiments. Perfect, that is. I don't know. I didn't pay you, right? To ask this question. So,
One-dimensional instead of three-dimensional.
yes, so, yeah, perfect, yes, right. I actually need it. So the shape of the input, if you look at it, this shape this is, thanks for explaining that, this would be, I think it's the batches, but I never thought about it. I always ignored this first one. So the shape of this thing is 64 times 3. This is the shape of the input. And it gets more complicated there, but what I need to feed into the last layer is one-dimensional. So what I do is I create this three-dimensional, or I take this three-dimensional cube, and then I just flat it, so it's just, I don't know, it's flat. Well, it's just, sorry? Yeah, the vector, perfect. Yes, exactly. This would be a three-dimensional array or matrix, I don't know, and I need to have a vector, and that's what flatten does. So it's just, again, a technical thing, and I need to have it here, right? Because what comes in is, wait. Right, what comes in from here is something like a cube or a three-dimensional matrix, and I need a vector to feed this into this last dense thing here. It needs to have it. Okay, training results, disappointing, you see? It might have worked, but it did not. So still bad. It could have worked. On some days, I mean, it's all worse than I'm telling you. It's not deterministic, this thing. Depending on the start initialization of my network to be trained, it sometimes works and sometimes it doesn't. Sometimes this works. Sometimes with the 2 layers, I actually get 100% accuracy. It could have worked, yes?
Sorry. If you have a 3D data set, let's say matrix, 3D matrix setting, you flatten, what is the criteria to create the array? What is the origin? How do you choose this? Can I just take the 3D data and randomize them and then just put in an array? Because it's crucial for the convergence of this, how you flatten the data, or are you...
The question, if I get it correct, how do I flatten the data? And if it's at all...
What is the criteria to do that?
Just do it. Just any random way. And then what follows, of course, needs to be a correct training for this deterministic flattening. How we flatten, it doesn't matter. How we do later, that matters. So we don't know how we flatten. At least I don't know.
Okay, but let me ask you this question. Okay, you apply the same flattening to any source of this
Yeah.
method, the same one.
Yes.
If you change the way you flatten the
Yeah.
data in a different way, do you have a different response to this algorithm?
Oh, wait. Possible. So the question is, does the way I flatten the whole thing influence the result? That's possible, but so it's not something that we influence, and I don't expect to have big differences. So I think the flattening thing, we just do it, and then later in the next layer, we just have to like match the way we flattened it. So the next layer is the thing that actually has to be smart. Maybe it's not a good answer. I'm not quite sure. So I'm confused. What did I tell you? Oh, I claimed, without having a proof here, is that this could have reached 100% accuracy. but it did not in our example. And I have somewhere I have a notebook that actually achieved it. So, well, so let's say we found something that actually like achieved this. Then what we would do is to check the whole thing on the full data set. So let's see, we found the architecture, which we have not, and then we will check the whole thing on all the training data. Wait, did I do this? Why did I do this? I'm sorry, I'm not seeing it. Oh, here we are doing it. I was lost, sorry. Don't execute any of this, right? So don't do it. So what I'm doing now, I think I didn't properly explain it before, is that I'm splitting test and training data into different fractions as before. So this time we have test data 20% and training data 80%. And you probably know, but the idea behind this is I train with 80% of the data, like try to make the network learn, and then later I test with 20% of the data. And this is just to make sure we just didn't overfit and it just works for the data we were feeding in, but also for the other data. And there's dispute, like how you should split. Should you do it like 60-40? And this is also just opinion, I would say. I did 80-20 because I only have 400 data sets to train, so I didn't dare to like sacrifice a lot of the data for testing. So this actually takes on Azure 15 minutes because the model is complex, and we're not running it. It's the 2 hidden layer model, and on a good day, which is not today, we could get something very good accuracy. You see that? I actually achieved that one day. I don't remember when. That's quite big. This is 79% on that model. And then what you can do when you train the whole thing, there's an evaluate function. You put in the data that you want to evaluate. This is the training data. So this should be really high. And the training data, it has an accuracy of 96%, which is really good. That means like 96% of the data is good. But then, as I said, you split between training and test data. And then I feed in the test data. And now the accuracy goes down to 71%. Do you think that's a good result? That's hard to say, right? I mean, how could you? But then let's say you're driving in your Mercedes, and it tells you you're in the 50 zone, but you're in 30 zone. That's not good, right? 70% is not good. It's not good. Even saying that our test set was very small, and then the overall training set was also very small, this is still not a good result. We can do much, 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 much better. So we're doing it now. And I think I have to speed up, but I don't know how. Now we're getting to the much more interesting part. So we know all the basics. We prepared everything. We have more than half an hour left, which is good. And now we're coming to convolutional neural networks. And, well, I have to scroll up. And they work like this. You have many, many, many layers, like the classical ones. You have many layers. You again feed in something. I stole the image. That's why it's not a speed limit sign. You have many layers. Those are all hidden layers. And at the end, you again have a fully connected layer that does the prediction. And again, it has, in this case, 1, 2, 3, 4. It has 5 categories. This is the thing with the most likelihood. And horse is unlikely. Same thing, but this time you have many, many more layers. And as maybe you didn't experience, but I told you, if I took in 2 layers, it took me 15 minutes to train. 1 more layer, probably an hour. But this thing uses some tricks to actually make it possible to have that many layers. And you have different kind of layers. It's also different. Before we just saw fully connected. You have convolutional layers. I will explain them. You have, this is just activation. We can ignore it. You have pooling layers. And you have them stacked one after the other. If time permits, I will show you 2 other setups of those convolutional neural networks. But this is just different architecture. But technically, it's again the same thing as you saw before. I will show you. This time, you're totally invited to execute the code. As you see, we are now importing new kinds of layers. Let me see if I can still execute. I can. Good for me. We have input, same thing. But now, what happens now is you take the input. This is the input. This is something like that's pretty broad, like, well, however you would describe this shape, and you slowly turn it into something that is of this shape. That means you're reducing the dimension of your input, but you have like a lot of outputs from that. That's very abstract, but at least that's the idea. And also like the abstract ideas, the longer this gets and the narrower it gets, the more semantic information it carries. This is all about technical thing, like this is a real image and gets more abstract and more abstract and more abstract. And this is very hard to understand. And even looking at the mathematics, it doesn't help at all. So what I did, I again stole an example. What is this? Dog? Right, dog. So if this is your input, and you feed it through convolutional layers, what it does at the first step, the first convolutional layer, is this. Or could be this. And what you see, the color is gone. Like all the 3 color channels, they are merged into one. Color is not important for it. At least not at the level that we use it as humans. So it merges all 3 layers of that dog into one, but now it applies, I don't know, obviously 14, which is unlikely. Maybe I cut off some of them. Would be more likely that 16. It creates 16 or 14 representations of that dog that are much more abstract. But you still can see the dog, because what it does on a technical level is it applies a filter kernel, something that you might know from, I don't know, Photoshop or something, where you apply a filtering operation to an image. And the parameters of that filtering transformation, of that kernel, that's to be learned by the network. And if you're familiar with image processing, some of this, which maybe this, they look like a sharpening operation. Some look like a blur operation, which is hard to imagine because this is already very blurred. And what operations are performed on that image? It's learned by the network. And on deeper layers, this is just the first layer, this gets much more abstract. You don't see anything anymore. You can see like how the pixels are distributed, and that might mean something. But on deeper layers, it's just like a representation that you no longer like intuitively can grasp. So this is just the first layer. Maybe, I mean, the filter operation, how it works, it's surprisingly hard to even visualize it. I could simplify it by lying, and I will do that for you. Let's say you have an image with just, I don't know, each of those cells is a pixel. And now you go over it with the filter. Well, let me change the color here. Black. You go over it with filter, and the filter typically has a kernel size, which in this case is 2 by 2, which is not uncommon. And what you do is you like, for example, add each of those pixel values by a certain amount, and then you divide it by something else. I don't know. Possible. That would be like a filter kernel that, if you do this, if you add them all up and then divide them by 4, what kind of image operation would this be? I don't know. Is it blurry? Is it? Some people are nodding. So that would be an operation that's totally feasible, and to be learned by the neural network, that would blur the whole thing. And then once it done this, so it created a new value here, up here, new value. Once it done this, it moves it over by stride value, which could be 1, but mostly is 2 again. So you move to this one, then you perform an operation on this, and you create the next pixel here. This is just like image processing. But the interesting part is like how this is processed is completely learned by the network. How does this look like? It looks like this. So, oops, sorry. This would be the first block of convolutional layers. We have 3 after each other. So this is already 3 hidden layers, right? A lot. And you have 4 by 4 kernels. I was drawing a 2 by 2 kernel. This is 4 by 4. And the stride, like how far you move it with each step, is also 4. And this outputs 64 by 64, because it's still the same size, because the input was 64 by 64. But this time, we were applying 33 filter configurations. So the tensor that gets output is 64 by 64 by 32. So something that's flat like this, we made like very wide. It used to be 3, but now it's 32. So that's what we do. Why we do this, I don't know, because that's what turned out to be nice. So because it's now just deeper, and we want it like more narrow, there's a downsampling layer in between. And what it does, it takes a large image and makes it smaller. Done. And the idea behind this is to reduce data sizes, and at the same time, for reasons that I'm not fully aware of, it's set to reduce overfitting. So overfitting means it works for the training data, but not for the test data. And if you do this, people say it reduces overfitting, which is questionable because there are a lot of approaches that don't use it, and they still are better. So it's all just what professors say in their talks. So, and what it does, how it does it, it's called max pooling. You could also do average pooling, but this is max pooling. And how does it work? Very simple. You have a 2 by 2, I don't know how you call it, something, 2 by 2 max pooling filter. And you look at this thing here, and you see the 6. That's the max. This is the result. You go over this, you see the 8 max. This is the result. Again, 3 max and 4 max. And this is, if you imagine this to be an image, this is the scaled down, downsampled version of this image. And it's called max pooling. And by the way, I have links to more detailed explanations. But if you click on them, you will find that the authors, who are from Stanford, they explain it a very similar way. So they say, why it works, we don't know. We doubt it works. That's what people have been doing. Try it out. Maybe it works for you. So it's not at all a settled science or something. OK, here's my max pooling layer, 2 by 2, as I said. Now, something to reduce overfitting again is to have a dropout. That means with each training batch, I drop out a certain amount of nodes. That means I don't train them. I just pretend they're not there. And 50% is common, but I'm using 25% because I don't know why. 50, I could have used 50. But I thought 50 seemed to be high for me.
Is there a reason why you went for a 2 by 2 as the output at the end instead of, say, 3 by 3?
So the reasoning for those sizes here, right? So why is it 2 by 2? And why is this up here? Give me a second. Why is this 30? Why is this 32 things? This is just, not quite sure if I have it. This is just described here. So that there are different approaches, like how to process images. This is an academic paper from 2014, which means it's ancient. It's totally no longer valid. It's 3 years old. You can forget it. But this is how they describe the network here. And they had very good experiences with it. That's why I'm doing it. I'm just like re-implementing what they say in their paper, which is actually readable. And as I said, they use dropouts, as I'm doing here. They use the convolutional filters, small ones. That means, I think we have something like 4 by 4 or 2 by 2. I don't remember. They could be much larger, but that's what they are proposing. It's quite deep. I mean, typically it's between 16 and 19 layers. And you saw before, 2 layers were too much for us. 16 to 19, again, is too much. but you have something like 10 layers. I'm doing it because it's described here. I will promise that I will show 2 other approaches that are both better because they are newer, that do it differently. So, sorry, dropout, I showed you. Technically, it's what I said. You do it because you want to prevent overfitting. And overfitting, again, means it works well on your training data, but bad on data it has never seen. And then you keep on adding blocks. While you do it, you get deeper. So first, we had 32. Now we have 64 of them. And we get deeper, and we, again, downsample. So as shown as the explanation in the first image, we're actually doing exactly what's described up here. Sorry for the scrolling. So we become deeper, but also more narrow. And more narrow is what the downsampling does. Deeper is this is what the convolutional layers do, and this is what the downsampling does, like reducing the size. Again, why it works, no one knows. And this is not like a lame excuse. It's actually the truth. So now, what do we do here? We again set up the model. I'm a little bit afraid to do it because it takes time. You might start it if you want to, but I will just show results. So I'm training, what am I training here? 30? No. Yes, I'm training 30 epochs here. And you see it has a hard time learning, but you see a lot of movement. It goes down, and you might lose trust, but you should not. It's still not good after 30 epochs. And then I keep on training and training, because I knew it would eventually work. And now we have 98% of accuracy. Accuracy, I don't know. How do you pronounce it? Accuracy? Yeah. I'm German, I'm sorry. Good, thanks. And this is something that TensorFlow provides us, this image thing. There's the TensorFlow, I forgot the name. TensorFlow, does anyone know? The thing that creates this? TensorBoard, thanks, TensorBoard. It's a TensorBoard. So I used the TensorBoard to check how the training worked. And at the beginning, it looks bad, but then eventually, it should sort of match the RMS prop way of optimizing. But, well, that's very hard to see here, if at all. So, but the accuracy is very high.
What's being optimized between epochs? What's changing? Where's it improving?
What's this? It's accuracy.
Yeah, so why is there a trend for it to go up after each epoch? What's it, is it saving something it done in the previous epoch?
I'm not quite sure that I get the question. So why is it going up? Is that so? Yeah, that's a very good question. So a lot of the setup of the network is fixed. Like the dropout is fixed. The flattening thing is fixed. The downsampling stuff is fixed. I have to scroll a long way, I'm sorry. But what is not fixed is the parameters of the convolutional layers, like how they filter. That's not fixed at all. So each of those like parameters is a variable in our function that we need to optimize for. So the parameters of the function that we're trying to optimize, they're huge. They're huge parameters, much more than 2. I don't know, maybe there are 1,000, maybe 1,000,000 sometimes. And that's what we're trying to optimize. And what we are measuring at the end is that we stick in a picture, we know the right result, and then we check how accurate is the prediction here. And we do this while training. I know some frameworks, they can't do it, they only show the loss, but we can show while training, we show the accuracy here. And if it was 1, that means each prediction is perfectly right. And we are very close. And you see the evolution over time. This is the overall error, which should be in the other direction. And there you see how to do it yourself if you want to. Now we are already in the validation part, and we should be. And I didn't train that, I know. Will it still work? I pre-trained the thing. But it says the training accuracy in the end is 1. That means perfect. But this is not important, or not really what I was shooting for. Oh, shit. Sorry for using bad words also. But what we can also see, and this is much, much more important, this is the test stuff. And this is the important value. This is 90%. I had it up to 95% accuracy, which is very good for that size of data. But that means that is much more powerful than the model that doesn't use convolutional layers. So 90%. I prepared this because obviously I messed up my notebook here. So what I'm doing, I'm randomly choosing 10 samples just to make this a little bit more, I don't know, impressive. And those are the predictions. And if the prediction is green, it's right. So the truth for this is 4. The prediction is 4. It's obviously right. It's a little bit boring because each of these 10 predictions, I did this morning, so to make it look good, is actually right. So this is obviously, it's a very good test set because each of those it could predict correctly. And this is very hard, I think. This is very hard. It could be a 30, right? But all the predictions it did right. So probably you're no longer like typing on your laptops anymore. And you shouldn't because it would take a lot of time. What we do now is we save the model, which Keras allows us here. I'm just saving it. It's very easy, model save. There you go. I can list it, and if you count correctly, 1, 2, 3. This is, no, it's this one, but same size. Okay, this is 32 meg, right? 32 megabyte. For a model of, I mean, that's not a complicated model, but it's big already. So what I'm doing, for reasons I will tell you later, I upload it to this nice service transfer.shell. They give you free space for 14 days, and it's saved from here on. I did this for 2 other approaches, and I did this to use it to predict on real data, on real images that I either took a photo of using my cell phone. And that is the interesting part. And just watch, because executing it is not interesting. And it's in the same library, so it's all up there, so you don't lose anything. Oh, spoiler, sorry. I'm sorry. Okay. So this is all just installation. I did this morning. Hopefully, it's still alive. They kill them after a while, so all your data is still there, but the variables they are lost. It's not killed, which is very good. I'm very lucky. So let's have a look at the images that I actually did from the real world. They look like this. Give me a second. And as you can see, they're much harder, right? Much harder. I have no idea. I think it's the zoomed out version of this. It should be a 50. Where's the other hard one? It's not easy to even see this. And this, what is it? It's a 70. And what is this? And I also did something very mean. I took a picture of this number. How do you call that? We call it Hausnummer. Is it house number? Is that a thing? Yeah. That's a house number. Obviously, it shouldn't be like recognized as a 70. Otherwise, your car thinks you can drive 70 here. And if the officer asks you, what's wrong with you? And you say, yeah, 70, not good. So I did this. I did this because I'm evil. And I want to like make it as hard as possible. Then I did something like this, very high contrast change. I didn't train with this data at all. We have it like tilted, also not in the training data. This is impossible to see. It's just nothing. It's just dirt. And also, it's not centered. So all the data that we used is the detail view. And this is just an overview picture. But I wanted to make it as hard as possible. So this is something somebody drew. It's not even a real thing. So how many of those with the thing that we just trained, how many of those do you think it recognizes correctly? That's the fun part now. How many? 50? Oh, no, no way. Not 50%. OK, I'm looking bad now. It's not your fault. So I'm making predictions. If you want to, There you go. That doesn't look good. They barely fit, but they do. So we have 15 images, and 5 of them we get correct. This one, surprisingly, this one. Well, this one, it's debatable. I mean, it predicted, yes, that's obviously a 70, but it's not. So that's, is it right? Is it wrong? I don't know. And this is also correct. But you see all the things that are not zoomed in, that are not a detail view. It cannot detect. This thing, it's impossible to detect. This thing also is not a detail view. Not a detail view, not a detail view, not a detail view. And it can't detect those. Yes, question?
Yeah, like where you say you don't want the house number to be detected, but like there's no way for the model currently to say this is not.
Right. So good point. I messed it up. So you say it's impossible for the model to tell the 70 from the others. I made mistakes, and I will sum them up later. Yes, but good point. You're completely right. So let's try a different architecture. And again, if you ask me, why is it like this? I can only point to this paper. This is the inception model done by Google people. And the idea is to have a non-sequential model. So you put in some input, and then you have so-called, is it easy to see towers? Maybe this. Like you spread the model. It's not sequential. And then eventually you merge the results. And that's called inception model. And there is a pre-trained inception model by Google that does outstanding things, but I did it myself, and it's okay-ish. So this is, I also have a notebook up there where you can see how it is set up, like in detail, but this is how it looks like. It makes different predictions. I was very surprised that it actually could make the right prediction on this. I wasn't able to, but it could. And it didn't see this as the, which it shouldn't.
Well, it did see, it saw it as something else, which is not. That's why you need a category which is like not.
Right. Right. That's already a solution. I'm missing the not category. I'm missing the, this is a stop sign thing. I'm missing all the other signs. So totally correct. Bad mistakes. It should predict something like, this is not even a sign. But I don't have the category, and I don't have it trained. So it doesn't work. And also, what I don't have trained is like translation invariance. Not in the training data at all. So it's no surprise it doesn't work. Still one more example. And this is like, oh, I shouldn't use swear words. So I'm not doing it. This is like the hottest stuff in the area of convolutional networks. And again, if you ask me why is it like this, I can only point to this paper, but I can show you the basic idea. You still improve the depth of this. You go to like 150 layers. And it's still possible to train that many layers because you're introducing shortcuts. Why this makes it easier trainable, I have no idea. And I think they also don't have any idea. They just saw it. They just made experience, and they saw when you do like this, you feed in data in the normal convolutional layer, and then you feed it into the next, but you also bypass the whole thing for whatever reason, and then at the end you just merge them again. You can have much deeper hierarchies, and you get much better results. It's also skipping the final fully connected layer, which we had before, which makes the model really small. But also to my very big surprise, let's see if I can see it, how small it actually is. Sorry, I need to scroll.
Do you know why you want to skip your final layer?
Good question. The question is, why do I skip the final fully connected layer, which before was said to do translation invariance, and it was mandatory to work at all? I don't know. But that's the way it is. I had to cope with that. So no good explanations. Let's see like how big this thing is. And again, it's not like making false excuses here. It's not like, I don't know, but the others do. It's rather like, we all don't know. And especially don't know. So let's compare sizes. So the first thing that I looked at was 32 meg. This thing is the Inception, the tower thing, the Google thing. It was 400 meg. 400, and this thing here now, the residual thing that I'm showing you now is 1, 2, 3, 1, 2. That's 2 meg, right? So it's tiny. And I think it's mostly because it's also lacking the fully connected layer at the end. But let's look at the results. So it has this simple trick. It's very deep, and it skips complete training layers every now and then. Oh, and it also uses something called batch normalization, which is completely the others don't use. And this is, I can't completely explain it, but this is a way to even reduce overfitting stuff and then also make the model learn faster. So it doesn't use like a dropout or something, but instead uses batch normalization. And is explained here if you really want to know. But that's also new. So let's look at the results. And that's how they look like. It has 50%. So it has 50% of accuracy. More than the others. But other than that, I don't see a pattern. So I couldn't explain why or what it sees wrong and what it sees right. I don't know. But it at least has 7 of them, and it's the smallest model. So it's a very small model. It's very accurate. I think I have 10 more minutes. So I'm coming to what I messed up. So first, is it readable? I can zoom in here now because I didn't train in translation invariance, which is totally bad. So if you drive with your car and then the sign is somewhere, and I didn't train that. It has to be sent out all the time. But this is due to, because I don't have the training data. I was very lucky to even find any training data, but I just don't have that training data accessible. It's also not robust against background. I saw that in the examples. If the background turned to blue, it could no longer make it out as the right sign. It has false positives, like the 30 address number. It's not clear against, it's not robust against unclear signs. My 50 up there looked like a 30, and then, well, it should have said I don't know. But there's no I don't know category. This is too low. 64 times 64, this is not even C64. It's just nothing. It's just too low. I don't know. Oh, yeah, right. When I was zooming out, you just couldn't see anything anymore. If it was distorted, like tilted to the side, it still couldn't handle it. I can't answer the questions. Why do different architectures give so different results? I don't know. I don't know if there's someone who would know, but I doubt it. I think it's just trying it out, but I'm not sure. And even if I did this many times over, and I trained the same, sorry, I'm standing in the picture, I'm sorry. I trained the same architecture over and over again, and I got very different results on the test data. Sorry, yes, on the test data. I'm not quite sure if this is just normal, but it gave me a bad feeling. So what does that mean if I actually want to fix it? That is just toy, of course. I'm not working for the automobile industry. It's just, no worries. You can safely drive your cars. So I'm not doing it. I should do something because I don't have a larger training set. I saw people doing this. You have the image, and then you artificially create new variations of that image by moving things around, by changing the background color, by adding distortions. And this is something I could do. And then introduce a category that says that is not a speed limit at all. And even a category that says this is not even a sign. This is just nothing. This is a 70 printed on my hand or something. Maybe I also have translation invariance, which could be added into the training material. Translation invariance means it doesn't matter where the sign is. Higher resolution, which for sure will result in longer training duration, and then try other architectures. Just to give you an impression, the stuff that I did, it was almost impossible to train on this machine. It's an i5, 8 gig machine. And it was very hard to actually train that on the Azure cloud. So people who do this with a lot more money, they use much bigger machines. They use a lot of GPUs. So by this nature, I'm just restricted to how complex I can make my architecture. So I think this leaves us with 5 minutes of questions or a head start for lunch. Whatever you want. I don't blame anyone if you leave now, and I see people leaving. That's totally cool. So I take questions now. Yes?
Just a bit curious about your observation about the resolution, because I don't find that terribly convincing. Let me explain. There's a similar exercise done to recognize handwritten digits, right? And it uses a ridiculous resolution, much less, right? And those are handwritten digits, so in a way, the problem I don't think is the resolution, the problem is the background. So I guess probably if I would have to come up with an industrial type of application or solution for this, you would have probably with a pipeline where you use something like OpenCV to take out the background, where you focus on the side. And then at that point, the resolution would be absolutely fine.
So the argument of this gentleman is that the resolution should be fine, 64 by 64, and then that to circumvent situations like these, you would rather zoom in before and then keep the same result.
Please do so quietly because people are interested in the answers to the questions.
So the answer is, I think you're right. More questions or comments? Yes?
How come that every time you get different results if you do the training?
So the question is, how come that every time I do the training, I get different results? The answer is, I don't know. This is part of the questions that I have myself. That I get different results, it's because I get different trained models. But why they are different, I can't explain. I'm sorry. I would love to. If you can, tell me. Yes? So the question is the filters that are applied that you saw in the filtering of the dog. Can you pre-supply them? I think you could, but that's not the idea of the whole thing. The idea is that the neural network learns the correct filtering. But you could. I'm not quite sure if people do it, but of course you can. They are by definition predefined, but probably random values. But you could. Yes? The question is this always feed forward? What I'm doing, it's always feed forward. But there are also recurrent neural networks where you have loops, and you also have nodes that have short-term memory. I think they're also called short-term memory networks. And this is something that I didn't try out, but people who did say it's better. So yes, it's there. And this would be in my next steps. Use a different architecture, use something like this. But of course, I mean, why not do this, yeah? So people try it out, and they get good results. Yes?
Yeah, I don't know. First, I would like to say that I don't know in the neural networks what is the best answer to everything, because people really don't understand how many of these things work. But have you played with the optimization of the parameters themselves, the architecture being selected by an optimization algorithm? Because I know that some people are like using like a meta level in which the parameters of the network itself are optimized, trying to increase the accuracy. Because when people say, "Oh, I know the architecture I have to use," sometimes I'm like, "Do you really know, or is just like this and check if it works?"
So the question is, if I've played with all the other parameters, like the optimizers, which again also have parameters that you can tweak, and other things, and I have not. And the main reason is limited time. I do this manually. I type it in, I try it out, and then I get a result, and I do it again. But also know that people with a lot of more machine power, they learn, well, they train networks, or no, how should I put it? They do something like a meta thing. That's what you said, right? You try to learn what are the right parameters to set up my architecture, and you have a system that learns that for you by trying them out and then feeding back the error. But that's just brute force. I mean, what you need is a lot of machine power. But I have this thing, this i5 here, and not even a GPU. What you need is a lot of machine power. But I think that's what people do. Yes.
Can you give some hints on like the project planning and estimation type of stuff that might be relevant to trying to do something like this to somebody who hasn't done it before?
So the question is about how do I estimate how long it takes, and oh yeah, and how and make promises on how good I'm going to get. I wouldn't do this because I don't know. Maybe there are other experiences, but I think it's just I had no idea if this would work at all. So if I had promised this to someone, I would be under great stress, which I actually did because I processed talk before I even tried it. So it put me under great stress because it's not like a programming. I'm a programmer. So you get a task, and it's hard to estimate, but eventually you get it done. And this thing, you don't know if it works at all. And then how good it will be. So I don't know. It's more like fiddling around. I don't know. It's not even science. I know what it is. I'm sorry. Bad answer, but it's the best I can give. Yes?
So you tried to remove colors, and if so, did you find that colors were meaningful?
So the question is if I removed colors. I did not. But we saw on the convolutional networks that the colors disappeared after the first convolution. They sort of like went into the convolution in ways that, I don't know, are hopefully meaningful. But completely making them black and white, I don't know, maybe that's even a good idea to like normalize them better and take away overfitting because I'm not interested in colors. That's a very good point. And that's very, very inexpensive. That's a great thing to try. I should, yeah, good point. Yes, maybe find a question because, you know.
Have you had success with applying these sort of architectures to different problems outside of image recognition?
So the question, the question that I understand, is it advisable to use this on anything else but images? And I would say, I don't think so, no. I think these things are specifically being designed to work on images, but I don't have experience. Maybe people apply that to other problems, but I did not, and I don't know if it works. Do you know? Do you look like you do know? No? Okay, good. Good, okay, thanks, and then have a great lunch and great conference.